today what I would like to get through, there's a few things that I'd like to get through today. So I don't know, some of you may have noticed yesterday afternoon I got busy uploading stuff when I got home, finished recording some videos and stuff up there about some basic polynomials. May look like there's a lot of work there, but it's just a lot of algebra, adding, subtracting, identifying features. We'll play around with some of that this morning as I'm doing some of the further examples. And you may have seen on Google Classroom last night, I posted something saying, have a crack at those by Wednesday for me. Starting off with, I want to show you this. So today what we're going forward into is this idea of actually sketching polynomials. So I just want to start you by having a little look at this, the mathematician's dance, right? I love this. Now, absolute values, there's x squared, x cubed, 1 on x, there's our hyperbolas, negative 1 on x, log, base ax, exponential graph, y equals sine, cosine, and circle. Right? Thinking about the center line of that little human being there being the y-axis and his shoulders being the x-axis. All right? You can see all the dance moves. All right? Graphing math is all about just remembering what dance moves we're pulling out. All right, and I've got a little image there for you as well, so you can see some of your dance moves, and I love them, all right? And I'm going to be doing a lot of fake... to do what, circles? The hyperbolas, where it's like, and whatever it is. But we'll get there, all right? So what I want to look at today is how do we sketch, and not just quadratics or cubics, but polynomials in general. And remember, a polynomial is just something that has many terms to it. So I'm going to start off sketching polynomials, but we're kind of going to talk about in terms of starting off with cubics and then looking at a few other higher degree polynomials. So when we came back to sketching straight lines and sketching quadratics, the most important features that we wanted to think about were what was our x-intercepts, what were our y-intercepts, and then explicitly with quadratics, where is our vertex or where is our turning point. Right? Like I said yesterday, when it comes to a parabola, a quadratic, right now you are expected to label its turning point. You have to label the vertex. With every other polynomial that has turning points, we don't have to label them yet, right? By the time we get into year 12, we're going to have the skill set to label those points, but that will come in year 12. Is that okay? So we're looking for y-intercepts, x-intercept if it's a straight line, or intercepts potentially if it's curvy, remembering that discriminant helps us with quadratics to figure out if we're actually ever crossing an x-axis or not. So our y-intercepts. Our y-intercepts, well, they're just, if we were to look at a polynomial, and if we were just to look at that constant term, so that end term of a polynomial, we know, oh, that was dodgy, you can't even see that anymore, but that random plus c. Remember, from that random plus c, that's going to give us our y-intercept. And that was the same with straight lines, same with quadratics, same with every single type of polynomial that we deal with, right? Polynomial. Exponential functions, change that, and we'll deal with that later on, but pretty much every single other function, that random constant that's in there, is going to be our y-intercept. Our x-intercepts are when that whole polynomial is equal to 0, right? Much the same as what quadratics. So when our function equals 0, whatever x value makes it equal 0, that's where we're going to cross our x-intercepts, right? And that's why we did all that work with being able to factorize and use quadratic formula, because it points out these bits of information. Having a look at this one here, for example, we got the polynomial of x equals x minus 4 outside of x, and then x plus 2 all squared. Is everyone happy with that? And then x plus 2 all squared, I can rewrite that if I wanted to as x plus 2, x plus 2. And when we look at that we know how to read off when that's equals 0, because to make it equal 0, I need to put 4 in the first bracket, and then everything is multiplied by 0. And then I put minus 2 in. And it's important to understand when we have equal solutions. Okay, equal solutions important. When we have two equal solutions. I'll take that even further and say, so an even number of solutions, I'm going to say equals a bounce. When you have an even number of solutions, it equals a bounce. So I want you to, when I would say bounce, we're talking a bounce off an x-axis. Is that okay? So at the point minus 2, this curve, whatever it looks like, it's going to bounce off the x-axis because there's two of the exact same roots. And we saw that with parabolas. When it was x squared, it bounces off the x-axis at the origin. Just the graph of y equals x squared. It starts at the origin and grows. Remember that? And if we just shifted it to the right, that would be like x minus 2 all squared. And when we shifted that to the right, the parabola, the whole graph, it just moved. That vertex still sat on the x-axis. It just moved right. Yeah, Natalia.
So when you did 0 equals x minus 4,
Yep.
x plus 2, and you wrote down x equals possible, is that the thing where you factorize it again and then you make all of them like the opposite?
Yeah. So like I didn't factor. I don't need to factorize again because it's all in factored form. But remember, that's just three numbers multiplying together. And when I multiply three things together, how do I make that equal 0? One of those things has to be 0. So what do I need to put in the first bracket to make it 0? The opposite.
So without doing what you did yesterday where you like, I think you did like an extra step where you showed us how you got to that. In our assessment, when we're like doing our working out, can we just jump straight to doing that?
Yes, 100%. And again, it will depend on the question. Sometimes there'll be some questions where you can't, where you will need to factorize first. And that will be quadratic expressions. So it's something, hey, in the form of ax squared plus bx plus c when it's given in that expanded form. Or simple quadratics where you take a common factor of x out first. Okay? So moving on. Is everyone okay with that so far? It's just we need to know the zeros. That's really I wanted to put, and that. The behavior of endpoints helps if I scroll this down too. So when I talk about the behavior of the endpoints, I'm talking about where do the arms, so the very ends of that graph go? In what direction do they go? The leading coefficient, what do you think that means? Cool. All right, so just off to the side here. If I have some random polynomial, let's make a random polynomial up. P of x is equal to x plus 3, x minus 2, x plus 7, and let's go to, undo that. Let's go negative 2x minus 3. Cool? Do you agree that's a polynomial?
Yeah.
What would make that a polynomial in your mind, apart from the fact I said it's a polynomial?
Many terms.
It's got many terms. What do you notice about the variable x? What is it not? It's not a power of something, is it? I don't have something to the power of x. I'm not dividing by x, am I? It's just x. So they're the two big things I'm looking for, because x isn't a power. I'm not dividing by x. That's okay to be a polynomial. What do you think the degree of this polynomial will be? And by degree, I mean, what do you think its highest power will be, Chloe? Yeah, it's going to be the highest power is going to be 4. Do you agree with that? And the way that we figure that out is we just multiply those first ones. X times x times negative 2x. So do you agree we're going to kind of get like negative 2x to the power of 4? I'm not worrying about the rest of the junk, because to expand that out, painful, doable, painful, but I don't really need to worry about the rest of the junk at the moment. The leading term, if I was to arrange my polynomial with the highest power, is minus 2x to the power 4. Degree 4. It's important that we know it's degree 4 because degree 4 is an even power, isn't it? Yeah? So if it's an even power, we're either going to be praising the Lord or we're going to be bowing down worship because it's an even power. That's the importance of knowing its degree. At the front, it's negative 2. What do you think that negative 2 is going to have an impact on? Evelyn? It's going to flip it upside down. It's going to give us something like facing down. So we know the behavior of the endpoints of this random polynomial here. It's going to be bowing down. It's going to have both arms going down because it's got an even highest power. Because the even highest power has the negative 2 out the front, that means both of the ends are going to go down. Behave like a parabola. What happens in the middle might change, but both the ends' arms are going to end up facing down. Is that okay? The negative 2 part, that is the leading coefficient. It's called the leading coefficient because it's tacked onto the thing that has the highest power. Cool? The negative 2x to the power 4, that whole bit there, that is the leading term. Remembering adding and subtracting like terms was any pronumeral and number mixed together with its sign, that whole combination of thing. So that's a term. When you look at that term, its leading coefficient is negative 2, and its degree, or its order, is the power of 4. Okay, the reason I said order, BODMAS. What did O stand for in BODMAS? It stood for order. Order is just an old school way of describing to what power is a number raised. So BODMAS says you do the brackets first, and then you do any orders. Other words, do any powers, and then you worry about the rest of the stuff. Is that cool? Is everyone okay with that so far? We need to be able to identify what's happening at the front of the degree, that highest power. We need to be able to find that negative 2 of every single polynomial to figure out if we are doing something that looks like a quadratic or if we're doing a Travolta curve. Is that okay? Have I lost anyone yet?
Wait, so what would the negative 2 be?
Negative 2, well, that means it's going to bow down.
Yeah, but then the 2...
The 2, just remember the 2, when we're talking about a parabola, remember the higher the power, the tighter the curve got. Yeah? So again, with any kind of polynomial, if you're going to multiply it by negative 2, negative 5, it's just going to mean it changes really rapidly. And the higher the number, the tighter it's all going to get because it gets stretched out really quickly. Because 2 squared is 4, but then if I have, so that's okay, but if now I have 5 of x squared, well 5 multiplied by 2 squared all of a sudden becomes 20, doesn't it? Can you mentally see how that gets stretched out really quickly? And that's what will happen there with that negative 2. That will either determine it gets really stretched out, really steep, really quick, or if it's really small, like a fraction, it blows out. Is that all right? I haven't lost anyone yet. The most important thing about that leading coefficient, the only thing we're worrying about that leading coefficient, is its sign. Is it positive? Is it negative? We want to know what the endpoints are doing because the positive negative tells us which direction they're kind of going. The degree, the power of it, tells us are they both up, both down, or following that Saturday Night Fever Travolta dance. Cool? I haven't lost anyone yet. Beautiful. Going back to that polynomial, what do you think its y-intercept is going to be? Hang on, so I'm going to throw... That's our leading term. Nope, it's not quite minus 3. Negative 2 is the leading... All right, so what do you think its y-intercept is going to be?
Is there one?
Well, there is going to be one. What did we say y-intercept was in general? The random thing tacked at the end, isn't it? It's all the numbers multiplied together. So you know how we multiplied the first term, the x's, to figure out what its degree is going to be? We're going to do the same thing for the y-intercept. So our y-intercept is just going to be positive 3 times negative 2 times negative 7 times negative 3. So our y-intercept is just going to be 3 multiplied by negative 2 multiplied by 7 multiplied by negative 3. 3 3s are 9, so that's negative 9. Negative 9 times negative 2 is 18. 18 times 7 is going to be 14 less than 140, so that's going to be 126. 126? What's that? How did I do it in my head so quick? I just looked at things that I can do. I know 3 3s were 9.
Yeah, but like the higher number.
Oh, like, so when 18 times 7, I know what 2 times 7 is. 2 times 7 is 14. 2 times 20 is going to be 140. And 18 is just 2 lots less than that. So that's why I did 140 minus 14 in my head. Does that make sense? Okay, we'll leave it. We'll just back me. Okay, so that polynomial, it's going to have both arms end up facing down because it's an even degree. It's got a negative leading term, and it's going to cross the y-axis at positive 126. We can just gather that information from looking at the polynomial, expanding out all the x parts, and expanding out all the constant parts now.
But what does that mean? Like, cross the y-axis at 120?
So you know your vertical intercept? So that curve is going to cross up here at 126 somewhere.
Oh.
All right, I just know the line goes through at 126. So when it comes to labeling features, wherever across my y-axis, I'm going to write 126. It's really long. Correct. Agreed. That negative 2 that's out the front there helps stretch that curve, which is why it ends up being at negative 126. We'll look at examples of how to draw that in a second. Yep. Does it move sideways? Do you think it moves sideways? Why do you think it moves sideways? Yeah. Well, we can see that it crosses the x-axis in multiple locations. But notice how none of those locations are evenly spaced above and below the x-axis. Like if I have a positive 3, oh yeah, it crosses at negative 3, so they're kind of evenly spaced. So that kind of starts to look symmetrical around the y-axis, doesn't it? If I cross through at negative and positive 3, but all of a sudden, when you look at those middle two, negative 2 and positive 7, well, they're not evenly spaced away from the y-axis, aren't they? So if I was going to ask you to make a prediction, do you think that this function, if we were to sketch it, would be an even function? No. Because we can, even function, remember an even function is something that's symmetrical around the y-axis. If this was going to be symmetrical about the y-axis, where it would cross, so remember it's x-intercepts, the x-intercepts for this one, so x-intercepts, whoa, that was dodgy, would be negative 3, positive 2, negative 7, and positive 3. Yeah? Do you agree with that? Oh, no, it's not positive 3, is it? It's going to be negative 2/3. All right, so this last bracket we need to be careful of, because that last bracket is when does negative 2x minus 3 equal 0? It's more, because there's a 2 in front of the x, it's not as simple as just putting in its opposite. So do you agree that then just becomes negative 2x equals 3? Yeah, I add 3 to both sides, and now divide both sides by negative 2. So x would equal negative 3 on 2, so which would equal negative 1.5, yeah? Is that okay? The thing now that I'm looking at in these intercepts that goes, this cannot be even, is that x equals 0, if it was even, it would have the exact same amount of split of positive and negative roots. Right? I've got my first root, my first x-intercept, sorry. Whenever I say the word root, I mean x-intercept. Right? Those two words are interchangeable. My first x-intercept is negative 3. If this was to be even, I'd also have another x-intercept of positive 3. But I don't. Or we don't. The second that you see that that doesn't happen, we can read straight away, this cannot be even. Because it won't reflect. We can then go through and algebraically show that. But it won't be, because it won't reflect. Does that make sense? Do I need to draw a picture of that for you guys to understand that? Yes? Yep. All right. Teacher's favourite friend, Desmos, here we come. Desmos, what am I graphing? Can someone call out for me again what my brackets were? Y equals x plus 3, x minus 2, x plus 7, negative 2x minus 3. Cool. We'll go like this. We'll go projector mode. Let's turn it to black to make that contrast nice. So you can actually see something. Done. Let's go here. Let's zoom. Let's change this. Let's go x-axis. Let's go negative 30 to 130. And let's go, oh, nope, silly Bradley. Negative 30, let's go negative 20 to 20. And let's go here. Let's leave that. And let's change this to, let's go more than 140, let's go 200. Let's go. All right. Whoa. I didn't want that to happen. There we go. I'll leave it. Cool. Is everyone okay? That's what that curve will end up looking like. Can you see how it's both arms down? It's bow down and worship. That was the impact of the negative 2 out the front. It's both arms going the same direction because it was degree 4. Can you see when I click on the curve? Not that you can really see that, but trust me, people in front row, you might see, that says 126. It crosses at 126, which is what we said when we found that y-intercept. Let's click on our roots. Negative 7, negative 3, negative 1.5, 2. They were everything we said, weren't they? Can you see those features there? Does that kind of help? Yeah. Now look at the middle. We said both arms down, but it's got this wavy stuff. See these points on the wavy, the turning points? I don't expect you to find them yet. That's the Year 12 fun, okay? I'm going to Command Shift for that. I'll add that to OneNote in a second. Is everyone okay with seeing that? Does that help tie together what we talked about with the polynomial just then? I'll add that picture in a second. Please remind me to do that. What's up? Oh, Saturday Night Fever. Odd powers are our Travolta curves. Even powers are our up and downs. Is that okay? I told you, we're going to do lots of dancing. All right. Cubics. These are the only forms ever in this course you'll be given cubics in. All right? You'll be given them in the form of x cubed plus c. Right? That's nice and straightforward. Right? X cubed plus c. That means the little s flick part goes to the y-axis. The plus c just means I'll move it all up or down. The k that multiplies out the front either stretches the curve out or compresses it in nice and tight. That's what that k, that would be the same as the a value in ax squared plus bx plus c. It just, how quickly am I changing? In y equals k outside of x minus a all cubed, what do you think this impact happens? What does this do to a cubic curve? When I put, yeah, moves it left or right, doesn't it? This second one here, y equals k, and then x minus a all cubed, it moves it a units left or right, doesn't it? So that, yeah, so at the moment, if this was x minus 7, it will move it 7 units to the right. And if it's x plus 7, it moves it 7 units. Because remember, you've got to put that opposite in there to make the bracket 0. Yeah. Yeah. So that second one, all it's doing, it's moving our cubic curve sideways along the x-axis. That little chicane, the little, I'm going to call it the wiggle. So that chicane, the part where it changes, it is now effectively to be known in our class as the wiggle. Right? The wiggle passes through the x-axis. Is that all right? And then the final way you'll be given cubics is in completely factored form, which looks like polynomials. And that means that wiggle doesn't necessarily pass through an axis anymore. That wiggle gets stretched out and happens because there's going to be lots of turns happening. Is that okay? Have I lost anyone yet? Beautiful.
In that, is the C still the...
C would still be in the y-intercept. All right? And in this final one, so in that second row, the y-intercept is going to be the value of a cubed. In that final one, a times b times c, multiplying those n things, will give you the y-intercept. Is that all right? Let's go look at an example of how this works now. Can we sketch the polynomial x cubed plus 5? So, before we go anywhere, you need to identify those 4 things for the moment for me. So we're going to sketch the polynomial x cubed plus 5. What would its y-intercept be, do you think? 5, thank you. It's positive 5. It's that random constant that's hanging out there at the end, isn't it? Cool. So its y-intercept is positive 5. What would its x-intercepts be? This one's going to be interesting. It's a degree 3. You're right. So it's got the cubic nature to it slash. I don't know how to spell Travolta. So, but you understand what I mean when I say Travolta. Chloe. Its x-intercept isn't negative 5. No. So its x-intercept. This one's the hard. Yeah.
Would it just be how it would be just an origin but at 5?
That's where the wiggle is going to end up occurring. But
is it like the square root the 3 of minus 5?
yes, yes. So we'll go through that. Its leading coefficient is positive 1. Yeah. So before I go anywhere, it's going to roughly off to the side follow that kind of cube. All right, that's a perfect. Well, it's not perfect, but that's a cubic curve, isn't it? So it's going to look kind of like that. But that curve has been moved up 5 spots, hasn't it? So it's going to end up looking something like that. See how it's that cubic, that chicane nature. Oops. I'll move that up. That chicane nature. But instead of the chicane passing through the origin, the wiggle passing through the origin, it's gone all the way up to plus 5. Is that all right? Can you see that? Because it's literally get the graph of x cubed, chuck it up 5 spaces. So we know that this value here is 5. We know that. The only thing we have left to label is what is that point there. Remember, x-intercepts happen when the polynomial or the function equals 0. So we just want to answer the question, when does x cubed plus 5 equal 0? Right? Well, that gives us x cubed equals negative 5. Yeah? Undo a cubic, you do its cubic root. So we want x to be the cubic root of negative 5. And remember, odd powers are allowed to have negative signs. So that's going to give us a value. Is that all right? And for the interest of being exact, that x-intercept there is the cubed root of negative 5. That's exactly where it crosses the x-axis. Is that okay?
So it only has one.
It only has one x-intercept, this one. That one's easy. That one was okay. It's the x cubed, move it up. You can see from the green graph from the right there, it's just been moved up 5 units. And then we just go, well, when do u equal 0? And I'm going to label that. Any questions on that? I can move on? Beautiful. All right. Sketch the polynomial 3 outside of x minus 2 or cubed. All right. That's that second option. We're going to give you a cubic. So what do you think is happening to this cubic curve? Is it shifting right or left?
Right.
It's shifting right. How many units right has it shifted? 2. How do we know that? Because look, it's x minus 2 or cubed. The opposite of minus 2? Positive 2. It's moved right. Can we see that? All right. So our y-intercept. Well, before I go anywhere, remember this is just 3 outside of x minus 2, x minus 2, x minus 2. Agreed? I can write it that way, can't I? The y-intercept, remember we said it's that last number. Negative 2 times negative 2 times negative 2 is negative 8. Is that going to be my y-intercept? So negative 2 times negative 2 times negative 2 gives us negative 8. What's hanging there out the front? The 3, which means this graph is all of a sudden stretched by the number 3. So our y-intercept, which should be negative 8, now becomes negative 24. So cause that 3 is out the front. It's multiply everything inside the brackets by 3. So our y-intercept is just going to be the value of 3 times negative 2 cubed, which is negative 24. This curve is crossing at negative 24. Okay? Multiply those end terms. Don't forget the thing out the front. Yep. Yep. The x-intercept is x equals 2, x equals 2, x equals 2. That's an odd number of repeated roots. Would you agree? It's an odd number. It's the same root happening 3 times, odd number of the exact same value. An odd number of the exact same value gives us a wiggle. Remember how I said where that chicane passes through the origin, I called that part the wiggle part? Didn't we just say this was an x cubed curve just moved to the right? So instead of wiggling through the origin, it's going to wiggle through 2. It's going to pass through the y-axis at negative 24. Anything else? The degree, I think we already established. We knew this one is going to be a degree 3 because it's x cubed. Yeah. Its leading coefficient is 3, isn't it? Yeah. Why do I say it's 3? Yeah, they're cubed. The leading term would become 3x cubed. Remember, x times x times x gives me x cubed, but I have this little sneaky 3 out the front, which makes it 3x cubed. So cause it's positive, we know our Travolta curve, its endpoints are going to be up here and down here somewhere. That's where it's going to end up being, yeah? So I'm going to draw that nice cubic curve. I'm not going to go through my arrows at the moment, but I know that's where my curve is going to end, because that's what a positive cubic curve ends up looking like. I've got to wiggle through the x-axis somewhere, so I'm going to go like here, wiggle through. That was dodgy, but that's okay. Do that, rub out that. See how I've kind of got that wiggle happening through my x-axis? What did we say that? I want to pause. Have you noticed how I've drawn the last two curves? I've drawn the curves, then I've added the labels. Because if I practice just drawing nice shapes and then add the labels, I can make my axis fit my curve nicely. It's very hard to do all the labeling and then draw a nice curve because you're like, oh no, I need to do this. Oh no, you know what I mean? It's like, oh, I needed to be there, but I'm... Forget the labeling till the end. Now I'm going to label. We said that was positive 2. We said that was negative 8. And last thing, P of x equals negative 24. Thank you. Negative 24. And finally, P of x is 3 lots of x minus 2 all cubed. Give my graph a name. Is that okay? Can you see how all that kind of is relating to those different bits of polynomials? We're looking for what our degree is doing. We're looking for what our dancing is happening. We're looking are we moving left and right. Is this going to be an odd function?
Yes.
Do you think? Looking at it, no, it's not. What did we say odd functions? What kind of symmetry do they have? They have point symmetry. So if I was to stick my finger at the origin and rotate it, that curve should land upon itself before I get to 360. Can we kind of mentally see how if I turn that 180 degrees, it hasn't hit itself yet? Because it hasn't hit itself, it's not going to hit itself. That's in neither. It's not even, it's not symmetrical around the y-axis, is it? I can't spin it and get it to hit itself before I get back 360, so that would be a neither function. Can you see visually how that's happening? We could algebraically prove that if we wanted to, but we can visually see it. How am I going for time? I've talked a lot. I've talked a lot this lesson, but are you finding it valuable?
Yeah.
Beautiful. All right, another curve. Sketch the polynomial, negative x outside of x plus 2, outside of x minus 4. So, interesting fun fact for you. What would be its y-intercept in this one?
Plus 2 times minus 4 is minus 8 plus, and then times 1, but it's negative, so would it be just positive 8?
No. I like the math that you did there, but it's not positive 8.
Would it just be at the origin?
This one is going to be just at the origin.
Why is that?
Why is that? I'm going to use your math to explain it. Everyone's comfortable that positive 2 times negative 4 is negative 8. But what's hanging at the front of both brackets now? The x. So that means anything I expand out in these brackets here, I'm going to multiply by x at the end of it. Does that mean I'll have any random term left over without the x variable attached to it? No. Because the second I multiply those out, I've got to multiply everything by x. There's going to be nothing that has no x associated with it. So its intercept is going to end up being 0 because there's no random constant term left at the end. The constant term would be 0 there. Yeah, exactly. So our intercept, our y-intercept, that's nice. It's going to be 0. What do you think our x-intercepts are going to be? Negative 2, positive 4, there's going to be a third one. 0. The x at the front, when it's 0, everything becomes 0, doesn't it? Which goes to prove our y-intercept is passing through 0. It's the origin. Because if it's got to pass through x equals 0, it's y equals 0. Does that make sense? We're all happy that that's going to be a degree 3, because we're going to be x times x times x. We can see that. Cool. What's our leading coefficient going to be?
Is it negative or 1?
It's -1. What gives it away that it's -1?
The negative side.
It's the negative at the front of the x there. Right, so what we have here is that -1. So let me go back a step. The degree 3 tells me it's that Travolta curve. Right, it's got to look like that. The -1 tells me that's a negative gradient. So the -1 tells me the endpoints start in that second quadrant and finish in that fourth quadrant. That would be a negative cubic curve. The opposite of the positive one, funny enough. All right? Now, here's the cool part. You ready? I need to pass through -2. I need to pass through 0. And I need to pass through 4. I'm going to just label them this time. I know I need to pass through -2. I know I need to pass through 0. And I know I need to pass through, hang on, let's undo that. 4 should be, well, go away. What's happening? All right. Now, I know I need to start. Now, my next question for you. Am I repeating any roots? No, I'm not repeating. None of these numbers are repeated. My x-intercepts, remember roots and intercepts, x-intercepts, same thing. None of my x-intercepts are repeated, are they? Because nothing is repeated, that means I just pass straight through. Okay, so I'm passing, so I've got to start up this top left and pass through -2. We'll finish this one off. Pass through, draw. I've got to pass through -2, don't I? But now I'm below the x-axis somewhere, aren't I? Do you agree? Now, the next thing I need to do is I need to pass through 0, don't I? So I've got to turn around somewhere and come up and pass through 0. But now I'm above the x-axis and I need to pass through 4. So I've got to turn around somewhere and pass through 4. Is that all right? All right. I don't care where those turning points are yet. All we need to figure that from here is I had to go from above the x-axis to below the x-axis through -2, but then somehow I needed to get back to 0. So I had to turn around at some point to get to 0, but then I also had to turn around at some point to get through 4 to finish down the bottom. Is that all right? That's the biggest trick about sketching polynomials. Where am I starting? Where am I ending? How do I cross through? When I cross through, I need to get back up. Or do I keep going where I'm going? Is that okay? All right, we'll leave that there. Great work, team.